Recording in progress.
Okay, the recording started. Yes, yeah, probably we should start then, would be my feeling. Okay, so let's start the next session. My name is Martin Weitz. I will be chairing the next this talk and the next one. So the first talk that we have is an invited talk by Hui Chao from Yale University. The title of our talk is Complex Lasers with Tunable Coherence. We are very glad that you came online or coming here online, and looking forward to your talk.
Okay, great. Well, first, thank you for the introduction, Martin. And also, I would like to first thank the organizer for this invitation. So today I'm going to talk about the complex laser with tunable coherence. So let me start with a very brief introduction about coherence. So we have, like, say, the first order coherence is about the, field correlations at different spatial locations and also time. So in particular, we have temporal coherence. That's about the, field correlation at the same place, but different time. There's a time delay of tau. Or we can have spatial coherence. That's about the correlation of fields at a different location, but at the same time. So typically, the temporal coherence is determined by the line width of the spectral width of the light, and the spatial coherence is determined by the divergence angle of a light beam. So in addition to the first coherence, there's also second order coherence. That's about intensity correlations at a different spatial location or time. So this is called a G1 or G2. So what make a laser different from a lamp is not the first order coherence, but the second order coherence. So even though typically laser has high temporal coherence and also spatial coherence, but actually if you spatially or spectrally filter like a white light source, you can also get a pretty good temporal coherence or spatial coherence by just making the line width narrower. But the second order coherence is actually coming from intensity fluctuation that can be reduced in a laser by gain saturation. So that is what distinguishes a laser from a lamp. That is a second order coherence. But in this talk, I'm mostly going to talk about the laser with a tunable spatial coherence. In other words, for a laser, they still have a good second order coherence, but what we are trying to tune here is a first order coherence. In particular, is a spatial coherence. So we all know that the laser has many, applications in, because it is very bright. It can provide direct, beam. It's very efficient in terms of power consumption, and also has very good spectral control. However, the laser has not been widely used as an illumination source for full field imaging, for laser projectors, for photolithography, or for holography. So why is that? The reason is because we have the speckle. Because if you consider a laser, with high coherence, spatial coherence, when the light goes through a scattering, sample or goes through a rough surface of some optics, the light can be scattered and then goes through different paths. Then they acquire random phase. And when those light interfere with each other again, they will produce this so-called random, grainy pattern, which we call the speckle pattern. So this is a big issue for, imaging, because it will hide the real structure we want to image. So what is the standard way of removing the speckle? Is to using like a diffuser, which is like a ground glass that has many scatters in there. And then shine the laser through it, and then try to rotate the diffuser. Because at every location, we can generate a speckle pattern that is a random grainy pattern, but it will change as we rotating the diffuser because the laser will hit a different portion of the diffuser. So now if we average all these different speckle patterns together, then we can reduce the contrast. So I'm going to show you a movie here On the left, it is a speckle pattern, individual speckle pattern going through the diffuser. On the right is we average over many speckle patterns, sum of them. So you see that as we sum over many speckle patterns, the contrast indeed is reduced. But the contrast scales at 1 over square root of n. N is the number of speckle patterns. So therefore, if we want to get a 3% speckle contrast, we need about 1,000 speckle patterns to average. And this will take a lot of time to average, so then this will reduce the speed for imaging. So what is our method? So let's first take one step back to see what is a laser. Why a laser can give us high spatial coherence. So we consider a cavity that's made of mirrors, 2 mirrors, and we have a gain material in between. So light is being emitted by the gain material, being amplified when it's propagating through the gain material, and then it's going back and forth, between these 2 mirrors, so they have more amplification. Right, and then a small amount of light will going out of one of the mirrors that produce a highly directional beam that have good spatial coherence. So then to reduce the spatial coherence, as I said, we're using a moving diffuser outside the cavity, right? So if you see what happens here is that we first make a very good laser with good, meaning high spatial coherence, and then we try to put a moving diffuser outside to reduce the spatial coherence. So rather than doing this, why not just put a diffuser inside the cavity? Then we'll try to make a laser that has low spatial coherence from the beginning. So we don't need to do this post-processing, or after the laser, we have to reduce the spatial coherence. So if we put many scatters inside the gain material, so what we got? We actually, when the light tries to emit it, it has to be scattered many times by many scatters, go through a random walk before they really get out of the gain material. So during this process, we see the light will propagate a longer path in the gain material, so they will be amplified more. So therefore, we don't need this mirror to trap light, to enhance the light propagation path length inside the gain material for amplification. We can just use this multiple scattering for this kind of enhancing optical amplification, and also provide feedback for lasing. So this kind of laser is called a random laser or mirrorless laser. So for those lasers, we can have low spatial coherence. Let me just show you a very simple example. We have a solution of dye. Then we put in the scatters in there, like titanium dioxide particles. And then we excite the dye with the second harmonics of a YAG laser. Then the laser emission, from this random lasing in the solution, will actually project onto a double slit. Then we try to measure what is a far field image pattern. So what we can see here is that if you have a spatially coherent light, the field from the 2 slits will be interfere with each other. At the camera, you will see fringes. But here we don't see any fringes. That means that actually the fields are uncorrelated at these 2 different spatial locations, meaning we have a low spatial coherence. So how this low spatial coherence is produced is because in this random laser, there are many different modes can laze simultaneously and independently. Each of them produce a random speckle pattern. If we add all the intensity together, because they're incoherent with each other, then we can have a low speckle contrast or low coherence. So this means that this random laser is actually, rather than previously what we show for rotating diffuser, you generate many different speckle patterns in series. Here we generate the random laser generate many speckle patterns in parallel. And when you add them together, you can reduce the speckle contrast. So this can, really make, high-speed imaging. But let me first show you a simple example here. We try to using a random laser illuminate an Air Force test chart, and then we insert a static scattering median in between the Air Force test chart and the, imaging lens to the camera. If we illuminate with a neon laser, we see a lot of speckles because of high spatial coherence or high coherence of this beam. But if we go to see a random laser with low coherence, we can clearly still see this, image here. So this actually has been used for time result microscopy with the random laser illumination. So this is done by a German group. What they show is that if you trigger this kind of like a random medium, they can have random lasing with a short pulse at a fixed delay time, and this can be used as an illumination of a transient process. They actually can get speckle-free imaging with only 10 nanosecond integration time. So that means that we can really do high-speed imaging without speckles using random laser as an illumination source. So, but the random laser I just show you here is actually with is a colloidal solution of particles in the dye solution. Dye, you can, does not have a, very long lifetime, and also this has to be optically pumped by another laser. So for practical random laser, what we wish to have a compact electric pumped laser, that have low cost and also long lifetime. So one way to do this, we can using like a semiconductor laser. For example, semiconductor membrane with a gallium arsenide quantum well in there, right? We can try to etch a random array of air holes, and then we can using a photonic crystal layer boundaries to eliminate the light going from other directions, so they only go from one side. So this is what we fabricate: a random array of air holes, in a freestanding membrane. We can electrically pump it. We can optically pump it. Then try to get a random lasing. But the problem is that because it's very hard to do this in electrical pumping to make a contact into this membrane, and also this structure is made by e-beam lithography, which is also costly. So therefore, we say we want to find a simpler solution. So what could be a simpler system that can give us this kind of compact, electrical pump, low-cost random laser with long lifetime? But before we answer this question, let's try to see how we can make a laser with low spatial coherence. What we need. From the study of the random laser, we know that we need a highly multimodal laser, meaning that to achieve this, we need about 1,000 modes that can laser simultaneously. This basically requires all these modes has similar lasing threshold, and also they have a minimum gain competition, so they all can laser simultaneously and independently. And also each of them will produce a distinct emission profile. So when we add all of them together incoherently, we can reduce the spatial coherence. So how can we do that? In addition to the random structure, we can also using a chaotic microcavity. So let me try to introduce what do I mean by a chaotic microcavity. Let's first consider a regular circular disk, two-dimensional cavities. Now, in this case, if we launch an optical ray, it will go through this kind of whispering gallery trajectory. Now, if we slightly moving the initial launching position, we still get a whispering gallery trajectory. So, in other words, there's a slight change in the initial location does not significantly alter the trajectory. However, if we consider a D-shaped cavity, meaning we're cutting a small part of this circle, then this cavity has a chaotic ray dynamics. What do I mean? I mean that if I start like a launch array, it will go through some path, and then if we start to change the initial condition, now you can see that the ray is completely different only after a few bounces. So that means a slight change in the initial condition will make a big change in the trajectory. So that means the trajectory is very sensitive to the initial condition. That's why we call the ray dynamics is chaotic. So this chaotic ray dynamics or regular dynamics will affect the spatial structure of the optical resonance in this cavity. For a circular disk, we can have this so-called whispering gallery modes that has high quality factor and a low lasing threshold, but they stay near the boundary of the disk. Then if I have this called D-shaped cavities, then we can have this modes spread over the entire cavities like this chaotic ray trajectory, and and also they can have very speckled output emission. So because of this, modes in these D-shaped cavities, no matter what is their spatial profile, they have a similar quality factor. So they have similar lasing threshold. And also because they are spread over the entire cavity rather than localized near the boundaries like the circular disc, they have less mode competition for gain compared to whispering-gallery modes. Because whispering-gallery modes, they will compete for gain near the cavity boundaries. Here they can use the gain over the entire cavities, so have less gain competition. So that means we can have many modes lasing simultaneously. That can give us low spatial coherence of the emission. To confirm that, we actually fabricate, this D-shaped micro disc on a commercial gallium arsenide quantum well wafer for the semiconductor laser diode wafer. So by photolithography and wet etching, we make this kind of disc. The radius is about 100 micron, and then we can put electrical contact on the top and the bottom to make electrical injection of the current to obtain the gain in a quantum well. So what we have seen here with electrical current injection, we can achieve the lasing at room temperature, and then we collect the emission from the side, from the street, segment using a multi-mode fiber. And then at the output end of the fiber, we see a more or less smooth, emission profile. This actually means we have low spatial coherence. Why? Because if on the same disk, if we make a whispering-gallery, type modes in a circular disk that lays, then the emission you only have a few mode lasing because of strong gain competition. So then this emission still have very good, spatial coherence. When it goes through a multi-mode fiber, which is similar to a diffuser, you will generate a speckle pattern. So this basically shows that we can really just, using a conventional laser diode, just to modify the cavity shape, we can really get low spatial coherence. And for this kind of D-shaped laser, what is the advantage of this compared to like a bright LED or a thermal source that has low spatial coherence? They also have low spatial coherence. But here, this D-shaped cavity has much high brightness. We define the brightness in terms of photodegeneracy, meaning the number of photons per coherence volume. So for D cavity, this photon degeneracy is about 4 orders of magnitude higher than the bright LED and 5 orders of magnitude higher than the thermal source. It is slightly lower than the superluminescent diode in terms of brightness. However, this superluminescent diode usually they have fairly good spatial coherence, so they still can generate, speckles, noise. So that means the D-shaped cavity can have a high brightness and a low spatial coherence, and that will be useful for speckle-free imaging. So we indeed actually using this kind of low coherence source, laser with low spatial coherence for this kind of massive parallel phase-sensitive interferometric confocal microscopy. Actually, this spatial coherence gating provides 18,000 continuous virtual pinholes. So let's try to see 2 pinholes here. There's 2 different spatial locations. There's, there's like, have a different, they are incoherent with each other. And then they are actually imaged onto the sample, and also a reference arm, like a mirror here. And then the light coming from the sample will overlap with the light reflected from the mirror. They will coincide at the camera. But if we consider the first pinhole, they have a signal from the sample, overlap with the reference from the first pinhole on the camera, they can interfere. But if the signal from the second pinhole was accidentally gets due to scattering getting into the first pinhole, because they are incoherent with the reference beam from the first pinhole, so they cannot interfere. So this will reject the light from the second pinhole to the first pinhole because they cannot, interfere with the reference from the first pinhole. So this is why we can use spatial coherence as a way to reject the signals, and then that gives us this confocal microscopy. So using this, we actually was able to achieve really ultra high speed, this kind of 4-field confocal, interferometric microscopy for in vivo quantitative macroscale physiology. In particular, we're able to achieve about like a 2D frame rate more than 1 kilohertz with a lateral resolution of about 2 micron and axial gating depth about 10 micron. We can also get axial resolution here too because of this confocal gating due to the spatial coherence. So this allows us to visualize and also quantify the cilia-driven surface flow and also cilia beat, frequency in tadpole, which is the animal model, which is widely used at the Yale Medical School here. So to summarize the first part of my talk, I want to show you that if we consider the illumination source for full-field imaging, what we care the brightness. We also care about spatial coherence. And typically, thermal light source or light emitting diode, they have low spatial coherence, so they can produce speckle-free imaging. But the problem is that they have a low brightness, so they cannot allow high-speed imaging. But if we're using the lasers, they are much brighter, so they can have, can have a much shorter integration time for imaging. But the problem is they have a high coherence. They give this kind of coherent artifact, like speckle noise. So what is really required is we want to have a high coherence, high brightness and a low coherence. And I show you two examples, a random laser and a chaotic microcapillary laser that can combine the high brightness of a laser with a low coherence of the lamp, which is really ideal for this full-field imaging, which allows us for high speed and also speckle-free. So this is the first part of my talk, which I said that the speckle is a problem for imaging, but the speckle can also be useful. Why is that? Because the speckle is generated by interference of the light scattered from this kind of particles. So if the particle is moving, those speckle will change. So it's very sensitive to this kind of motion of the particles. So give you one example here. This shows a coherent laser reflected from the thin skull of a mouse. So you see that we see all this speckle coming from this, interference of those, scatter light. But if we show the speckle contrast as a function of different location here, we can clearly see these blood vessels. Why is that? It's because when we have this, blood cell flowing in these blood vessels, they will scatter light. Then the speckle pattern will quickly change with time because of their motion. So if we have a finite integration time of our camera, in those regimes, we have to average over many different speckle patterns. So therefore, the speckle contrast is low. But in the other regime, the scatters are, static. So you have a high contrast because you only have, you have a single speckle pattern. So therefore, the speckle contrast can tell you the motion of blood flow that has been widely used for the so-called laser speckle contrast imaging. So if you see what we really wish, we wish to really to switch the spatial coherence of a laser so that we can have a low spatial coherence for illumination. Then we can see the structures without the speckle noise. And then we also want to switch to high spatial coherence that allows us to using the speckle contrast to prove the dynamic process. Actually, people have already tried to do this using two light sources, LED and a laser. But the question is, this two source has very different brightness and also the divergence angle. So you need a separate optics, setup to align them. So this is very, very bulky. And what we want using a single laser, but we can switch the spatial coherence. But what is the challenge? The challenge is that when we switch the spatial coherence, we want the emission power is almost the same. And we also want the light is coming out almost in the same direction. So we don't need to realign, this kind of, light emission. So how to do that? We can using this so-called degenerate laser cavity. So basically you can see here, this is basically a degenerate cavity, meaning that we have two mirrors, then we put two lenses in between them. They are in this called a self-imaging configuration. Well, F1, F2 are the focal lengths of these two lenses. So you can see that, if we have the gain material at, one end mirror here, when they emit light, and then the light after one round trip will go back to the same position. If you have another position light emit there, it also go back. So this is a self-imaging. So because of that, we can have many transverse mode that, spatially, separated. They have almost the same frequency and also almost the same quality factor. So therefore, they can lay simultaneously And then we can have multi-mode transverse mode lasing. And because they laze independent with each other, when the total emission at output is the sum of the emission from all these different lasing modes, then we can have low spatial coherence. So now if we put how we can get into high spatial coherence, we put an aperture at the focal plane between the two lines. Now if we close this aperture, then you see this emission from different part of the gain material has to be in phase to form a plane wave, so they can focus through the aperture, and then they can get lasing to reduce the loss. So that means in this case, we have a single mode lasing that can give us a high spatial coherence. But because of this single mode, have the same overlap with the gain material as a multi-mode lasing, so the total emission power is almost the same. So therefore, we can just close this aperture to switch the spatial coherence without much, a loss of the power. So we have collaborated with a Weissman team showing that for a solid state degenerate cavity laser, we can actually vary by change the aperture. We can changing the number of transverse lasing mode from 1 to 320,000. But we only have about less than 50% change of the power. And this is in a sharp contrast if you try to do, like spatial filtering using a pinhole outside the laser cavity. Because if you're using a pinhole outside the laser cavity to try to do spatial filtering, the power will scale linearly with the number of modes. So if you want to reduce the number of modes from 300,000 to 1, your power will reduce by 5 order of magnitude. But here the power reduction is less than 50%. Simply because we put this aperture inside the cavity for this kind of active spatial filtering. So we also, using a VEXL, vertical external cavity surface emitting laser, we're using that as a gain module to build a degenerate cavity configuration. And then in this case, what we have, actually we are able to tune the spatial coherence, to have a high or low speckle contrast, without changing the temporal coherence. The temporal coherence can be seen as the line width of the laser emission spectrum, which stay almost the same as we switch the number of lasing modes. So we can tune the spatial coherence without changing the temporal coherence. And then we're using this to imaging the heartbeat of a living tadpole, because the tadpole is animal model of heart disease. The tadpole is embryo of a frog. So if you see here, this is the head, this is the tail, and then the heart, it is here. So using a low spatial coherence illumination from this degenerate cavity laser, we can clearly see the structure of this heart. We can see, this ventricle and artery. And then if we switch to high spatial coherence, we have this, really a speckle noise. Then we can do this, using speckle contrast to see the blood flow in the heart. So here I'm going to show you a movie. On the left, it is a structure of the heart. During this, you can see how the shape changes during the heartbeat. And on the right, I show the speckle contrast. The yellow color meaning low contrast, meaning you have more blood cells in there to introducing, this kind of motion that can introducing the induce a low speckle contrast. So you can see that indeed we can clearly see during the heartbeat how this heart, the geometry or the shape changes, and meanwhile how this, this kind of blood flow or this kind of blood cells moving from one chamber to another chamber. So this allows us to really study this kind of, this kind of function. There's a function of the heart with the, the shape or the structure that allow us to really understand these heart activities in those kind of, tadpole. So with that, I basically show you that we can really switch the spatial coherence, right, to do the to do this kind of bimodal imaging. Next, I want to show you another, application that's about fluorescence microscopy. Because fluorescence microscopy, you said why the spatial coherence matters. Because we're doing fluorescence that have low coherence, it should not have, any speckle. That's true. But typically, we are, exciting those fluorescence using a laser beam. Because the laser beam has very narrow line width and also control the frequency that allow us to really match the absorption spectrum of some fluorophores. But typically those, excitation, pump intensity here, if you see here, if we're using a laser to excite the fluorophores, then we can clearly see this kind of pump intensity modulation due to this kind of, surface, roughness or goes to some scattering materials. So therefore, if you have intensity modulation of the excitation beam, then when you see the fluorescence intensity variation in space, you don't know where that's coming from. It's coming from the fluorophores are strictly homogeneous or because of pump intensity variation in space. So therefore, we want the pump intensity to be homogeneous, but typically this, we are using a green laser as excitation for most fluorophores. So that means we need to using a green laser with low spatial coherence. And typically it's hard to find the green laser directly because the gain material is hard to really, have very efficient gain material at a green frequency. So typically people do is a frequency doubling of a near infrared laser. So here we want to using a degenerative near infrared laser so that we can have many, modes or low spatial coherence at the fundamental frequency that's a near infrared and frequency double to generate a green laser with low spatial coherence. But what is the issue? The issue is that because we have many spatial modes, the power in each mode is low. If we want to frequency double it, it will be efficient, will be low. And also, we cannot really tightly focus this, output emission because we have lower coherence. So we cannot enhance the local intensity by doing a sharp focusing in order to enhance the second harmonic, generation efficiency. So how to solving this issue? We try to do intra-cavity second harmonic generation. We put the nonlinear crystal inside the degenerate cavity so that we have a higher intensity. So here shows our configuration of a degenerate cavity with the gain material is a medium, vanillate disc that is optically pumped by a diode laser. And we put a thin, KTP crystal as a, for second harmonic generation near the other, mirror here or close to the output coupler. So in this case, when we try to do, when we try to pump harder, we see a sharp threshold for the fundamental, emission intensity as a function of the pump power, because it's about raising threshold. And when we measure the second harmonic emission out of the cavity, we see a quadratic increase here, as we expected. So now, if we try to see what is a speckle contrast, if we illuminated the fundamental beam to a diffuser, we see the speckle contrast is about 2.5%, which means the number of transverse mode that lays simultaneously is about 1,600. Now, if we illuminate with the second harmonic signals, right, the green light to a diffuser, we see even smaller speckle contrast. That's about 1.7%. That means we have about 3,500, spatial modes, and that is really surprising. Why? Because as I said, we think in the degenerate cavity we have many different modes laid independently. Let's consider one of them has K1. This will generate 2 K1 through this nonlinear crystal. Another one is a K2 that's generated 2 K2, right? So now you can see that, because these two modes are incoherent with each other, and the second harmonic generation is a coherent process. So we should not, at most, the spatial the number of spatial modes for the second harmonic, frequency is equal to the fundamental mode, right? Because you cannot get more than that. But clearly we see we have more spatial mode for the second harmonic generation compared to the fundamental frequency. Why is that? That's because each mode has their coherence time. The coherence time is larger than the round trip through the cavity. So therefore, if you consider the light going through that's a nonlinear crystal for one passage, this passage has a very short time. During this very short time, the different modes, they remain spatially coherent with each other. So therefore, we can have this, some frequency generation from two different spatial modes give us K1 plus K2. So therefore, we can have many more spatial mode for second harmonic, signal compared to the fundamental light. So that's why we can have a lower spectral contrast or lower spatial coherence. So because of that, actually, we are using this low spatial coherence green light for fluorescence experiments to excite a rhodomine 640 solutions. Okay, and then what we see, we try to compare with another pumped source, which is a diode pumped solid state laser. So in these two cases, because the fluorescence sample is homogeneous, we would expect to see some homogeneous fluorescence intensity. But for this, if we pump it with a diode pumped solid state laser, which has high spatial coherence, we clearly see these fringes for this fluorescence. This is because of this, interference of the pump light, because of this, reflection from the substrate and also from some imaging optics. This multiple reflection, they interfere with each other, give us this kind of rings and these fringes. So that actually vary the pump intensity spatially. That's why we have this kind of spatial, varying fluorescent intensity. But using this frequency double the degenerative laser emission, because we have low spatial coherence, all this, coherent artifact is gone. So we still see very smooth fluorescence emission. So this means we can remove all this coherent artifact for this fluorescence image. So with that, let me try to move to the last part of my talk, which I want to show you that actually tuning, we can not only need to switch the coherence low and high, we can also use this to tune the spatial coherence. And this could be useful for another application. That's called the matter surface, holography. Because in recent years, there's a lot of interest, okay, to make this kind of a matter surface hologram, because they are ultra thin, very compact. They have a really fine spatial resolution. They can give a large viewing angle, and also they actually does not have a high order diffraction. But here shows one example. This is a metal hologram made of this densely packed silicon nanopillars. If we illuminate with a laser beam, we should generate in a far field like a holographic image is like a star. So you see now this star has a lot of intensity variation inside. It's not homogeneous, and this artifact is coming from the crosstalk of of this different silicon nanopillars, and also from fabrication defect and also phase dislocation. So what we want? So we want to really to remove those coherent artifacts. We can tune the spatial coherence of this kind of illuminating light. If the spatial coherence is low, of course that's not good, because we don't have any hologram, because we don't have any holographic image that can be generated, because holographic image is generated by interference of those diffracted light. But we also don't want this spatial coherence is very high that can create artifact. So now the question is, can we find an optimum spatial coherence for illumination that still allow us to have this holographic image to be generated, but meanwhile we don't have artifact? So to do that, again, we're using a degenerate cavity laser, but now we try to tune the spatial coherence continuously by moving one lens. So here shows the near field image of this emission. We can see that we can see different number of bright spots that's corresponding to different transverse lasing modes. So by tuning this this lens, we can vary the number of this bright spots, which is number of lasing modes that can vary the spatial coherence. But in the far field of this emission, where we illuminated the hologram, this illumination is still homogeneous. Now, because of all these bright spots, they are going to generate a plane wave that illuminated this metal hologram at different angles. So then what we can, because the hologram is put at the far field of this, output coupler, then they're going to generate a different, holographic image, which has a large, transverse, shift. If we add many of them together, we can smear out this, irregular intensity variation due to coherent artifact. So this is what I'm going to show you here, is that as we continue to tune the spatial coherence, we can see that the coherent artifact will be smoothed out. However, the edge is getting blurred. So if we plot the intensity, over this edge here, this white dotted line, we can see that we can find some optimal degree of spatial coherence, where we kind of reduce this irregular intensity variation artifact. But meanwhile, we can also get relatively sharp edges here. So this basically shows us that we can tune the spatial coherence, and then we can using that, to get a speckle-free holographic image. Okay, so this is my last slide. I want to show you why you think this would be better than temporal decoherence. You say I can also using a broadband, light illuminating a hologram. I can also smear it out. The problem is that if you have a different frequency of the light, they're going to generate a hologram with a different size. The size scale with the wavelengths. If you do off-axis holographic imaging display, all these different, holographic image for different frequency, they're going to have a diagonal, offset. So that means if you see this imaging done with a different wavelengths, you are going to have an offset of holographic image. And this is not as good as a spatial decoherence, which you will generate many different, holographic image of the same size. They just offset slightly, so that can still give you much smooth, edge blurring and also more homogeneous image there. Okay, so with that, I think I'll just stop here. Let me just try to. I have another application which I don't have time to talk about. Let me try to summarize my talk here. I basically show you we can design a laser with low spatial coherence for speckle-free imaging, full-field imaging. We can also switch the spatial coherence of degenerate cavity laser for this kind of, speckle-free imaging and also laser speckle contrast imaging to get more information. And finally, we're able to tune the spatial coherence, of degenerate cavity laser that allow us to do speckle-free holographic imaging display. So finally, I'd like to thank all the people who have contributed to this work. This is a list of people at Yale and also funding agency. And we also work with people in Israel, also in China, and also the companies here. So finally, thank you for your attention.
Okay, thank you very much for the talk. Questions? Just speak up, I think.
You have a question?
Yes.
Yes.
Yes. Yeah. Thanks a lot, Yui, for this wonderful talk. I'm curious about, the source in the degenerate cavities. I was wondering, you need to stay relatively close to threshold for avoiding filamentation, or you can preserve this, let's say, spatial incoherence even if you go very far from threshold.
Mm-hmm. Yeah, so the question is whether we have filamentation in this kind of degenerate cavity laser. Actually, we never see filamentation. But we do not pump really super hard. So if you see the threshold here, let me just show you one example here, is that we are pumping, it's actually still pretty high. So this kind of, here we're pumping close to maybe 10 times up to the lasing threshold. But up to there, we still don't see any filamentation effect. Of course, maybe there is something appears further, above that, but we have not seen that one here. Mm-hmm.
Okay, thanks.
Mm-hmm.
Further questions? So I have one question. This comment that you made at the end, that it's better to have low spatial coherence than low temporal coherence. Is it only for holograms, or is it in general for speckle-free?
It's also fairly general. So because if you want to say, as I said, if you have a source has a very high spatial coherence and a low temporal coherence, when you try to shine, like say, a light through a diffuser, what you will see is that you will see different speckle pattern, right? But they are almost the same, but just very expanded, radially for different wavelengths. So therefore, it's also not so good for separation. For speckle contrast reduction. Because if you even have a random scattering medium, you don't see this kind of a very regular diffraction pattern. You see a speckle pattern, but that speckle pattern for different wavelengths it will just radially expanding. They're not really like a good mixing.
Yeah. Okay. Thanks. Yeah. Okay. More questions? I don't see more questions, but this is also good that we can move to the next talk. So we thank Hui again very much for the nice talk. And
thank you.
So let's go to the next talk. So next speaker is Mr. or Mrs. Kuchera.
I'm Deba, and I will be presenting instead of Antonio.
Sorry. Okay. Yeah. Okay.
Okay, I will share my screen.
Yes.
Can you see my screen?
Yes.
And can you hear me clearly?
We can hear you. Yes.
Okay. Cool. Thank you.
Okay. So very good. Then we hear the next talk by Dayan Das on high parametric efficiency in laser cavity solenoid microcams.
Thank you to the organizers for giving me the opportunity to present one of our most recent works. I will be talking about the efficiency of laser cavity solenoid microcoms. This work is mostly done by Antonio and Maxwell Rowley, which I will be presenting today. Before showing the measurements, let me walk you through the setup briefly. So we use a 4-port microresonator with a Q factor of 1.6 million and an FSR of 50 gigahertz. And it is nested within an external laser cavity where erbium loop fiber is used as a gain medium. The external cavity also includes a few control elements such as the delay stage to change the length of the external cavity so that we can match it with the resonance of the microresonator. And also it includes a few waveplates to maintain the polarization inside the cavity. Now, to measure the efficiency, we need to first characterize the losses both in the external cavity and also on the chip, and then measure the power coming out of the drop and the through port, and make a ratio with the input power that's going into the microresonator, and which will give us the efficiency for both the through and the drop port. We start by characterizing the on-chip losses. It is important to characterize the on-chip losses so that we know what to take into account while calculating the on-chip efficiency and what not to take into account. The on-chip losses is a sum of intrinsic losses and the coupling losses between the ring and the waveguide, which can be obtained from the FWHM, the FSR of the microcavity, and the transmission from the drop and the through port, which can simply be measured by scanning a tunable CW laser through the resonance. So with this experimental value of the losses, we can estimate the theoretical efficiency. A set of coupled equation describes the system where A and B is the field in the microcavity and the external cavity. We define average power in the microcavity and the external cavity as EA and EB, and the intensity at the input drop and the through can be calculated simply from the stationary state. So simply the ratio between the EA and EB gives us the efficiency in the on-chip in the microcavity. Before going into showing you the experiment, I will show you the theoretical analysis that we did. The plot on the left hand side, this one shows the stability region where the soliton exists with the thick lines for different value of gain and detuning. The shaded area shows you the instability region of the background. This figure on the bottom shows the profile of the soliton for different values of gain. From blue to yellow, the value of gain increases, and the plot, the figure C, shows the efficiency for each of the states shown in B. It is important to notice that even for broader solitons, we have fairly good efficiency. Now to do the similar analysis in terms of experiment, we can change the gain of the external cavity either by ramping up the EDFA power or by simply changing the losses inside the cavity. We use the first method and ramp up the EDFA pump power, and by doing so, we see two distinct regions of existence of single soliton and two soliton. And in between, there is a region where both 1 and 2 soliton can exist. Yes. Oh, yes. So I forgot to mention that the plots on the left side is taken from the drop port, which is collected with a 90-10 beam splitter, and the plot on the right side is collected directly from the through port. Now we to measure the efficiency, we record the input power from the EDFA to the microresonator on plot A, and on the plot B, the plot B shows the drop output power and the through output power as we increase the 980 pump power from the EDFA. And then if we make a ratio between the input and the output power from each of the port, we can calculate the gain. And just like the theoretical results, we see similar trend for the through and the drop port with gain in terms of efficiency. To conclude, we evaluated the efficiency of laser cavity soliton microcomb both theoretically and experimentally. We obtain off-chip power of 11 to 16 milliwatt, including all the losses, both on and off the chip. We obtain a conversion efficiency of 25 to 30% from the through port and 40 to 46% from the drop port, which is a total efficiency of 72%. So thank you for your attention. It was quickly I tried to present our results, and this is our group. We moved from Sussex to Loughborough recently. Thank you.
Okay, so thank you for the talk. Questions?
Yes.
I have one question. Would you compare the efficiency of the soliton technique to the traditional one in generating frequency combs?
Okay, you mean the driven system?
Yeah.
Yeah, so the driven system has a few, like the conversion efficiency is very low, only few percent compared to this. And there are some techniques where they use the pulse pumping, where they have obtained up to 30%, but then their resonators are big, like they have FSR of 1 terahertz compared to us. We have 50 gigahertz, which is more useful for meteorological application, I guess.
Okay, thank you.
Further questions? I have one question. So, is a difference between such frequency comes in the efficiency compared to normal? As a non-frequency this should be quite comparable, isn't it?
Sorry, I didn't understand your question.
If you compare, how can you compare some of the efficiency of frequency comes as compared to a normal CW laser?
Yeah.
Is it comparable, or is there a big difference?
I have no idea about the efficiency of the CW, to be honest.
Okay, the feeling would be comparable, but I have no idea. Also. Okay, thanks. So if there's no more questions, then we thank you again very much. And I understood the last talk will be chaired by Jean-Luc.
Yeah, thank you very much, Martin. And I'm going to then introduce our next speaker. That's Massimo Giudici from the Université Côte d'Azur. And I'm just going to give him the floor. Please go ahead, Massimo.
Thanks a lot. So, do you see my screen?
Yes, very well.
And you see my pointer also?
Correct. Yeah.
Great. Okay.
I can see you and everything.
So thanks a lot to be here. It's almost dining time in Europe, so I will try to stay in my slot. So the subject of my presentation is going to be temporal localized structure in degenerate cavity laser, and I will show that in this kind of cavity we can obtain temporal localized patterns, but we can also engineer this cavity to obtain a spatial temporally configurable light. So these results is obtained in a frame of collaboration, which includes people from my lab, experimentalists, and particularly Adrian Bartolo, which is my former PhD student. And we interact a lot with laser engineer at the Institut d'Électronique des Systèmes in Montpellier, and with people manufacturing the sample, so Central Technology in Paris-Saclay. We had also strong interaction with theoreticians from Balearic Island and from Münster, even if I will not have time to speak about theory in this presentation. So the outline of my talk will be a brief introduction about localized structure, which is at the heart of our work. And then I will show that VEXEL, vertical external cavity surface emitting laser, are a promising spatial temporal laser platform where you can have a highly multimode light, as Professor Cao just showed at the beginning of this session. But we can also have the possibility of processing information and photonic computing. So there are plenty of nice things that we can do with these devices. And as an example, I will show the result we have obtained with these devices, namely time-localized patterns, and upon engineering these devices, spatial-temporal reconfigurable light. And I will come to my conclusions. So, as I said, at the heart of my work, there is the concept of localized structure, which is a concept that has been known for a while, and it's very ubiquitous in nature. So basically, localized structure are confined states appearing in nonlinear dissipative system having large aspect ratio and featuring bistability between different solutions. So there are two ingredients, as you may see, large aspect ratio to get rid from boundaries and lead the nonlinearity to lead the system. And second one is bistable response of the system. So what is interesting in these localized structures is that they are characterized by a correlation length which is much shorter than the size of the system. And for this reason, they are individually addressable objects. Now, this means that, for example, if you take a nonlinear optical cavity, they can be used as a bit of information for information processing, for example. And here I plot a figure that probably is the I don't know, 100th time that I show it, but it's very, very nice to illustrate the concept. Imagine that you have a 1D cavity where you have two kinds of emission. One is homogeneous and the second one is pattern. And in presence of large aspect ratio and by stability between two, you may have fronts that come and connect the homogeneous solution with one or two or several periods of this pattern. So you have a general multi-stability where you have all these red solutions that connect different periods of the pattern. And these one are localized structure. You can come here with a localized perturbation, switch them on and off them as information process, information bit. So in laser, so I'm speaking about laser not injected cavities, spatial localized structure has been observed in our group in 2008 by taking actually two VCSEL. So VCSEL is vertical cavity surface emitting laser, which are basically laser in form of disc, very thin in terms of the longitudinal size of the cavity, only 1 micron, but they can be very, very large area. Here, the one that I'm describing are more than 150 micron. And we take two of them and we couple them in face-to-face configuration. One was operated in a regime of amplifier. The second one was operated in the regime of saturated absorber. So why we did that? Because intracavity saturated absorbers enables to have a bistable response for this system, for this lasing system. Moreover, the fact that these lasers are so wide and short makes them really the definition of devices fulfilling the idea of large aspect ratio. Here we have a compound cavity, but because we made a degenerate cavity, a self-imaging cavity, we erase diffraction from light going from L1 from the first one for the second device. And in this way, we maintain the high large aspect ratio, which is typical of each individual sample. So what we obtained in the near field emission is this kind of emission where you see these bright spots are actually a localized structure. And you can come here with localized perturbation, optical perturbation, for example, and switch each one on and off. So you see, you can use this near field transverse emission of the laser as a blackboard, or you can, and you write on arrays a pixel of light. Now, we may notice that this is a setup which is widely used for obtaining passive mode locking. But this is not the case here, because for obtaining passive mode locking, you need the recovery time of the saturated absorber must be faster than the gain, while here we have the two devices which are the same, so you don't fulfill this. All that I showed here is stationary. So, few years later, and you have seen this in the last talk, the concept of localized structure or dissipative solid has been generalized in the temporal domain. Now, you understand that the large aspect ratio condition needs to be reformulated somehow, because we are not in the spatial domain anymore, we are in the temporal domain. So in some sense, now the box that you have is the longitudinal dimension of the cavity, and a way to reformulate this large aspect ratio condition is to say that your cavity round trip must be much larger than the bulk time scales of your system. So typically, if you use semiconductor laser, we have a gain recovery time which is of the order of 1 nanosecond. So it means that we need to have a cavity which have a round trip larger than 1 nanosecond. So what we did, we take advantage of passive mode lock regime, and we have shown that in presence of a saturated absorber, an intracavity saturated absorber, you get passive mode locking, but this passive mode locking appear in a multi-stable context when the saturated absorber has an high contrast. So as a contrast, I mean the modulation depth between the unsaturated reflectivity and the saturated reflectivity. So to realize this experimentally, we took a VCSEL and we coupled this with a commercial resonance saturated absorber, which has a contrast which is 60%. So we have almost 1 100% reflectivity when it's saturated, and only 40% when it is unsaturated. And in this condition, with a cavity which is 15.4 nanosecond of round trip, what we see is that the system is emitting all these passive molecular solution with different number of pulses, and this solution coexist together. So for the same parameter value, you can have the off solution without any pulse emitted, or 1 pulse per round trip, 2, 3, 4, up to the solution which has the largest number of pulses compatible with the size of the cavity. So you can see that we have something that is very close to what happens in space. The pattern now is a temporal pattern, and we decompose this in each period of this pattern. So this is the bifurcation diagram. You see that there is a current region, a pumping region for the laser, where all these solutions coexist. So it means that we can come and switch on each one of these pulses going back and forth inside the cavity. And this is what we have done here in this picture. So I use a spatio-temporal like picture where I show what is going on in a round trip, in a cavity, round trip after round trip. So in color scale, you have the laser pump, and the presence of the pulse is evidenced by this black trace. So what we have done in this case, we have initially just 1 pulse, which is emitted per round trip. And what we do here, we pulse the current, the pumping current, with a narrow pulse, a few nanoseconds, and we apply this synchronously with the cavity round trip for a few hundred of round trips. And you see that we switch on another localized structure, another localized pulse. And when we remove the perturbation pulse, we have now 2 of these pulses. We can also do the reverse with a downward pulse to erase one of these localized structure. So you see, we can handle each one of these pulses individually. And well, the setup is actually very similar to the preceding one. The point is that we obtain this result in a configuration which is not self-imaging configuration. And the problem here is that if we go to a self-imaging configuration, the saturation fluence of this VCSEL is too low with respect to the one of the saturated absorber. And as you may know, passive rocking requires that this ratio is much larger than 1. So we came to the conclusion that in order to try to implement a device, a laser device, where it should be possible to obtain at the same time temporal localized structure and spatial localized structure, we cannot rely on commercial devices. We really need to engineer our own device. So the question is it possible to gather ingredients for both spatial and temporal localized structure in the same laser? So such a device would be very interesting for fully developed spatial-temporal dynamics, for example, spatial-temporal mode locking, but it would be especially interesting for generated spatial-temporal localized structure, which are also called light bullets. Light bullets are very promising for a very efficient information processing, because if, for example, you can create a null optical buffer, as you shown here in this artist view of the setup, where you store information in the space, in the transverse space of the cavity, and also in the longitudinal dimension. So you have a large number of channels where you can store and process your information. So a device that is promising to realize this gathering together of these ingredients is the VCSEL. So VCSEL has been already introduced by Professor Cow. Is a vertical external cavity surface emitting laser. Basically, it's a VCSEL where you have removed the top mirror. So you have a gain mirror, or a half VCSEL, several ways to call it, and you couple this with a distant saturated absorber mirror, CISA. And okay, you obtain this device, which is normally used for obtaining passive molecular, as I said before, under the condition that the saturation we lost the connection. Do you hear me?
Yes, it stopped for a moment, but now we can hear you again.
Yeah, okay, so yeah, I have seen that my face was freezed. Okay, so yeah, you need to have passive mode locking using this device. You need to have this condition on the recovery time of satural absorber. And as I said before, you need a saturation fluence of the gain. It should be larger than the one for the satural absorber. But of course, I mean, this VEXEL device needs to be modified for including the condition we want, for having at the same time temporal and localized structure. So what are these requirements that we want to process? Well, first of all, we need a self-imaging external cavity. We need a broad area pumping to fulfill the large aspect ratio condition. And for obtaining temporal localized structure, we need a long external cavity and large modulation depth for the CSAM. Okay, so to implement this requirement, well, demanded a strong engineering effort, as you may guess. And at the end of the day, well, we use a device which was based on MOS-CVD technology, gallium arsenide, using optical pumping for assuring the best homogeneity, the best spatial homogeneity. So emission is typically at 1060 nanometer. And well, I'm not going through all these details. I just want to point out that the main difficulties is here that these commercial CSAM or common CSAM operating for passive mode locking are operating in fundamental Gaussian mode, thanks to some guiding like concave mirror. Of course, we cannot rely on this mechanism. We need to have self-imaging cavity. So we have excess losses, and for dealing with these excess losses, we had to play with microcavity. So instead of having a pure let's say gain mirror, we had some residual reflective brags on the top, and we reached this confinement factor of 4 with a microcavity bandwidth of 9 nanometer in order to be able to reach threshold with the large amount of losses. For the CSAM, as I said, CSAM contrast is crucial to obtain a bistable response. And to deal with this parameter, also we play with the microcavity of the CSAM by adding some dielectric pair, silicon nitrate. And this is the unsaturated reflectance versus the wavelength. When it's saturated, we reach 100%, so almost no losses. And you see that the contrast, if we are at the rest of the microcavity, exceed 20%. And you can also see that by detuning the resonance of the gain mirror microcavity and one of the CSAM, we can tune actually the contrast. We can tune the contrast and play with this parameter in an experimental way. Okay, so these are the samples. Now, what about the cavity? And so for the pumping, we reach a flat top pump profile having a diameter of 55 micron. We are injecting the cavity at the Brewster angle, which means that it is becoming an ellipse, which has a major axis of 95 micron and a minor axis of 55 micron. And concerning the cavity, okay, as I said, we need a long cavity, so we cannot use 2 lenses as shown before by Professor Cow. We need 4 lenses to have enough extension. And we use a telescopic, a nearly telescopic arrangement where the distance between the optical elements are given by the sum of their focal length. So the telecentric cavity or telescopic cavity ensure that you have self-imaging cavity after one round trip, but also makes the place the LPHYS' and the CSAM in a conjugate plane. And this is very important for saturating efficiently the CSAM. Moreover, we have placed a zoom here, playing with the focal length of L2 and 3 for having a demagnification of the gain mirror image onto the CSAM and improving the saturation efficiency of the CSAM. Okay, so this enable to reach self-imaging condition in cold cavity, but when you pump the VCSEL, actually you create a thermal lens and electronic lens on your gain sample, and these lens affect the self-imaging condition. So you have to recalculate the position of the optical elements, taking into account this thermal lens. And actually, you find out by using ABCD matrix that you need to shift two optical elements with respect to their telecentric configuration. So here it's the value of the distances. You see that they are corrected by this FTH, which is the focal length of the thermal lens. So we play with the position of this lens, L2 lens, and the correction with the respect to the telecentric position is a few millimeters. And the other optical elements that we shift is the position of the sesame, and the correction is only a few micron. Now, you may wonder, how can we verify that we are in self-imaging condition? And actually, we have established an observational criterion to place the lenses at the right position. This can be appreciated when you plot the waist of the fundamental Gaussian as a function of X parameter and for different value of delta Z. So I call delta Z the displacement of L2 with respect to the telecentric position, and the same for delta X, the displacement of the sesame with respect to the telecentric position. And you see that the waist of the fundamental Gaussian here is decreasing for delta Z negative when you are making your cavity longer, so when you are moving out the sesame, while for delta Z positive is the other way around. So exploring different position of delta Z, of the L2, and studying the way that the waist of the fundamental Gaussian was changing, we were able to approach the self-imaging condition experimentally, based on experimental criteria. Moreover, when you write the perturb ABCD matrix, you discover that the B coefficient of this perturb matrix, which by the way is what determines diffraction in the Fresnel eigency integral, depends on delta X, while C term, which determines the wavefront curvature, depends on minus delta Z. So you see, by setting delta X and delta Z, we have a way here to control diffraction sign and also the sign of the wavefront curvature. So now let me show what are our results. Again, I show what happens for different value of delta Z, and I concentrate here on what happens for the positive delta Z, which means focusing wavefront curvature. And you see that the waist of the fundamental Gaussian decreases as we make the cavity shorter, and at a certain point, the Gaussian beam gives way to this hexagonal-like pattern, which is a non-homothetic pattern, so cannot be explained in terms of guided modes. As you may see, we have an hexagonal-like structure in the far field. Still, you have to consider that we have a very strong axial component. Axial component is 90% of the power. If you hide this and you avoid the saturation of your camera, you discover that around there is this hexagonal structure of tilted waves. And when you look at the near field, you see clearly the hexagonal structure. So I'm going to concentrate on this structure to describe it. So this is basically the structure that appears when you make the system lasing in this condition for this value of the position of lenses and for position of the tuning in the regime where you have a multi-stable response. Now, you can isolate different components of the far field and make their image to check what is their shape. You discover that the central components has a Gaussian shape, while if you image just the crown, just let's say the hexagonal structure, you obtain a near field picture where you have double of the frequency, the spatial frequency that you have when you are monitoring the total output. So this means that all this structure is composed by waves which are locked together in phase and interfere and gives this near field. Okay, now theory, but I'm not going to talk about this, demonstrates that this appears thanks to a Turing instability, and the time scale, the spatial scale of this Turing instability is dictated by the value of delta x and by spherical aberration of the lenses.
5 minutes. Now, 5 minutes.
5 minutes, okay. So, from the point of view of what's going on in the time domain, this is just the time average picture. So what is behind this pattern is all these situations are in time domain. So you have actually coexistence between different solutions with 0 pulse per round trip up to 5 pulse per round trip. They all coexist and they have all this kind of pattern emission. So what is changing when you go from one solution to the other is just a scaling factor in intensity of the pattern. And you recognize this as a temporal localized structure that actually has a duration which is below our bandwidth, 20 picosecond. And this you see the optical spectrum, which has 1 nanometer full width as maximum, and the coherence time 2.6 picosecond. As I said, they are time localized structures, so we have time localized patterns, and to be sure, we can address them each one independently in the time domain. This is what we have done here by putting some pulses in the pumping current. Sorry, here we don't have the current, we have optical pump. So in the optical pump, we put pulses and we create one of these pulse after a situation where we have nothing, or we have one and we create a second one, and we can also erase them. Okay, so you are convinced that these are really temporal localized spatial pattern. So this has been published in this paper, and very briefly, because I'm really out of time. What happens on the other side? Well, on the other side, we have another kind of emission where we don't have any axial component. We have tilted waves in form of a ring in a far field. This far field broke down in spots when you put some something that break the O2 symmetry, for example, just this small tilting in the mirror. And what you may see is that the angle of this far field emission is increases as you decrease the angle, as you decrease the position of X. So, well, I don't have the time to go through this explanation about how they are originated. Let me just tell you that these are also temporal localized structure that can be switched on and off independently in the time domain. And so we come to the conclusion about this part, where you see that we have emission from spatial emission from the device, which is temporally localized, but is not spatially localized. And this you can realize if you detect each element of your pattern. You will see that the entire pattern is pulsating as a whole. Okay, so the spatial correlation of your pattern is as the size of the pattern. And you can see by an array of fibers, but you can also see by making some interferometer, by taking the two images of the emission and superposing them, you will see fringes, which means that we have a correlation length which has the size of the system. So the question is, okay, can you do something to the system to break this correlation? Can we enforce spatial localization? To do that, and I come to the last part of my talk, the idea is to put some chromium mask for shaping the gain profile on the transverse size of the gain mirror. Basically, you can put any kind of geometry for shaping the spatial landscape of the gain mirror, because you are in self-imaging. So whatever is going to lace, whatever its shape. Now we are interested in spots. So we use this kind of mask, and we deposit on the gain sample. And what we obtain is that thanks to this mask, we obtain decorrelated spatial emission. So for example, here, you see what happens. You see A and B spots induced by the chromium mask. And you see that, for example, here B is emitting one pulse per round trip. And for the same parameter, we have another situation where both are emitting, but A is emitting 3 pulses per round trip, while A is emitting only 1. So you see here we have broken the correlation emission. And we also, very, very interesting, you see that the orientation in the far field are different for A and B. So this allows to separate the emission of A and B, not only in the near field, but also in the far field. Now, if we plot the bifurcation diagram of each hotspot, A and B, you see multi-stability between different emission. 8 for A and B for 5 for B. And of course, just opening and closing the cavity, you can reset your initial condition and explore a different emission situation. Here, for example, you have A that is emits 6 pulses, while B is 5, here 1, 1, and so on. Now, to make it more controllable, let's say controllable, what we can do is to inject each hotspot individually, thanks to some addressing beam. This is what we have done here. So, for example, here we have injected a pulse in B without touching the emission in A, but also we can do the other way around, creating the spot in A without touching the emission in B. Okay, so this is a very basic demonstration of a spatial temporal optical buffer. It's we have that there are 9 states can be emitted by A in temporal domain, 6 by B. So if you combine on 2 channels, makes 54 different combinations of light states. And there are nice perspective for increasing the number of spatial channel. 8 is reachable just increasing the bump size. And in terms of the number of states that you can have in the temporal domain, it's enough that you increase the size of the cavity. So I come to my conclusion, but I'm not going to read them because I'm already out of time. And so I stop here. Thanks a lot for your attention.
Thank you very much, Massimo. Are there any questions? It's a very interesting talk. Let me ask one, since nobody's asking for the moment. What are the perspectives of compacting this kind of system? I know that your setup is quite complex and very bulky. Of course, I mean, if you integrate it, I'm not going to do. You're not going to do it right away. But the idea is: are there ideas for bringing it down to something like which is more compact and maybe monolithic or semi-monolithic through guides, wave guides, fibers, or whatever?
Yeah, I mean, in the transverse dimension, it's not really bulky because it's the same size. It's a microcavity. So, well, what is really bulky is the longitudinal dimension of the cavity. So, to have some compact. We still have to maintain the fact that the cavity round trip must be much larger than the gain recovery time. So it means that at the present stage, we cannot do much. Of course, you can imagine material which are much faster than the semiconductor material, for which you can decrease the size of the cavity, or to implement some, I don't know, slow light solution in the external cavity to increase the round trip without a bulky external cavity. I don't know. So far, we are exploring the situation with what we have. But yeah, maybe also the coupling with multi-core fibers is a solution. It's not going to shorten the cavity, but is making the system much simpler. So just to have an external cavity in form of multi-core fiber could be a solution.
Okay, thank you very much. Are there any questions, any other questions? If not, I think we should thank this speaker and all the previous ones as well. for being excellently well in time. We're closing the session at the exact time. And please remember, we start in half an hour. The next session will be chaired by Antti Moilanen, who's present. Antti, you can start even if I'm not present, as I told you. And see you in half an hour. Thank you. Goodbye.
Bye.